Our next speaker is Dr. Hogoboom from North Dakota State University.
Well, I appreciate the introduction, but I'm not a doctor. I should probably focus on my bachelor degree here first. Okay, so today I'm going to be talking about hydrogen combustion. Start out here with the overview, talk about my motivation, and then we'll go in depth on what hypergolic fuel is, talk about my methods. Then I'm going to go in depth on the hydrazine reaction specifically. 3 reactions that occur in combustion, both the predicted and observed reactions. And then I'm going to go through the exothermic and endothermic properties of the reaction, some stability factors, and we'll wrap up with my conclusions and where to go from here. So, okay, well, it looks like there's not a way to play this video. All right, moving on to the next one, motivation. So, determine the most efficient fuel to oxidizer ratio for the hydrazine reaction. Plan to determine the most efficient hydrazine/UDMH fuel ratio, which could potentially save on fuel costs as well as reduce unnecessary weight on board and facilitate the formation of less toxic byproducts that occur during the combustion of this reaction. So hypergolic fuel, what is it? Hypergolic is when you mix 2 things together and it ignites upon contact. I wish I had this video working here as well, but in this tube you see here is dinitrogen tetroxide liquid on the bottom, and at the top here is a dropper of hydrazine, and with just 1 drop of hydrazine in here you get a combustion as a flame. Pretty cool. It's ideal for spacecraft maneuvering because in space, for instance, if you have a satellite or cargo that you're trying to land on the International Space Station, you can do small amounts of fuel and oxidizer to better facilitate landing of the spacecraft on something like International Space Station. However, it is highly toxic, which is why one of the main goals is to reduce the toxic byproducts. Hypergolic fuel is really good because it has a high level of specific impulse in comparison to other fuels that we use, such as cryogenic fuels, which are more common with manned spacecraft. Hypergolic fuels we don't use with manned spacecraft as of right now because of the level of danger that they pose. So we'll talk about a few different types of hydrazine here. Hydrazine it has the best performance and it has the highest freezing point, which is a con, because with such a high freezing point you need to account for that and be able to make sure that it doesn't freeze. So that's extra weight on board. Whereas something like UDMH here has a very low freezing point, however it's the least efficient, so we need to account for that somehow. Methods and goals. All right. Plan to determine the trajectory of the hydrazine molecules by solving for Newton's second law. Also, we're going to determine the mechanism occurring during combustion using ab initio molecular dynamics. Use a PBE functional and a plane wave basis set with PA pseudopotentials. And we're going to determine the type of reaction based on the activation energy. If the activation energy is less than kT, which is roughly 0.025 electron volts, it's a spontaneous reaction. So there doesn't need to be excess or an out source of energy like an open flame or a spark doesn't need to be added in order for this reaction to start occurring. It just happens on contact. It's hypergolic fuel. So my specific reaction, the one that we'll be going in depth in today, occurred at 3,500 Kelvin. I use this temperature because some authors at astronautics.com claim that combustion occurs at 3,250 Kelvin. However, I did use a very small volume in comparison to what is realistic, just because I want to see this reaction occur at a fast rate. I want to see how it all works out. I did use 4 hydrazine molecules and 4 dinitrogen tetroxide molecules just as a starting point, the 1-to-1 ratio. So the first of the 3 reactions, which are the most important in my opinion, is nitrous acid formation. And if we focus our attention on the top left here, you can see the proton come in and attack one of the oxygen atoms, and then that nitrogen-nitrogen bond breaks, and we get a nitrous acid. And then we have NO2 on the left side, which will ultimately become another nitrous acid as well. That's the predicted mechanism, and if we look at the top right, we can see the observed is just that. Right here, we get our hydrogen and then our nitrous acid. It appears that this nitrogen-nitrogen isn't bonded, but this is because of the software that we used. It doesn't show those bonds if they're bigger than a certain distance, but it is connected at the starting point of this video. So this reaction was a fairly long one. It's 11 femtoseconds long. You can see it has some snapshots on the bottom of this reaction occurring. Just the first one is the nitrogen tetroxide, and then you get hydrogen come in, and then that nitrogen-nitrogen bond breaks and you get nitrous acid. So on to the second one. I should say that these 2 reactions don't necessarily happen in this order. They are independent. So this reaction is the creation of 2 hydrazine radicals. We have a hydrazine molecule on the right coming in and attacking dinitrogen dioxide, and then you get 2 hydrazine radicals out of it, which is important for our next reaction, which we'll look into. It looks like this one quit playing, but this is the observed reaction mechanism, and it does just that. The hydrogen here attacks this nitrogen, and we're left with 2 hydrazine radicals, which actually you can see on the snapshots, which I took on the bottom. This is the fastest reaction, about 4 femtoseconds long. Interesting to see creation. So on to the third and the most important reaction, in my opinion, the formation of water. We see this nitrous acid come in and attack the hydrazine radical, that nitrogen-oxygen bond breaks, and then the formation of water occurs, which we see in the observed reaction mechanism happen just as that. This is the longest reaction out of all 3. It's 13 femtoseconds long, roughly. Moving forward. Okay, so we'll dig into it now. We see here on this graph on the top left, this red line represents the distance in angstroms between oxygen 35 and hydrogen 8. And the blue line is nitrogen 23 and hydrogen 8. So you can see as this red line approaches 1 angstrom, that's where the formation of water occurs at. And this green line is total energy of the reaction. So we can see as a whole, the reaction is exothermic. If we were to draw a line of best curve, it's pretty clear that it'd be going down. If we zoom in on just this one formation here, we can see that as it reaches 1 angstrom, time step 104 is the first creation of water. We have this spike in energy, which shows us that the formation of water is an endothermic reaction that takes place within this exothermic combustion. And we see it again occur here at time step 114. We get another formation of water and then increase again. So the last one that occurs at 335, the third and final formation of water, we see that final spike there at the end, and then it reaches its state of maximum stability as far as the formation of water goes, and then you get a large decrease there. This picture on your top right is just a screenshot from the last step in the combustion, so time step 441 out of 441. And then this is a simulated mass spectra. It's not true mass spectra because it doesn't include charge, but I should say that it is just a screenshot of every time step, and all the species that are present are added up, and their occurrences are added together. So we see this nitrogen tetroxide at the very end is pretty much non-existent because it starts breaking down immediately upon the beginning of combustion. So conclusions, trajectory was determined, reaction mechanism was determined for a 1-to-1 ratio of fuel to oxidizer using VASP software. Determining the ideal ratio of fuel based off the known mechanism can allow for us to save on fuel costs as well as decrease weight on board, such as if we can have more fuel and less parts, such as the igniter, like in a cryogenic rocket, it's good. So the relative occurrences were also determined by the theoretical mass spectrometry. Where to go from here? I plan to do the same project here, determine the mechanism for the UDMH and nitrogen tetroxide, and then I would like to make a mixture of UDMH and hydrazine and determine that mechanism, and ultimately reduce or eliminate the toxic byproducts, which could potentially be a starting point using platinum nanocrystals, just off their known electrochemical characteristics as of right now. And if I can reduce or eliminate the toxic byproducts, what would be the end goal would be to reduce the energy loss. I'm assuming that if we get rid of this toxic byproducts, that it probably won't be as efficient, but I need to account for that one way or another. Some acknowledgements would go out to Dr. Dimitri Klein and Dr. Yun Han. I would take questions now.
Questions? If no questions, we'll go on to the next speaker.